Bom dia a todos. Sejam novamente bem-vindos ao nosso seminário do Programa de Pós-Graduação em Física da Universidade Federal do Ceará. Hoje esse é o seminário inaugural, a primeira aula do primeiro seminário do ano de 2022. E nós temos o grande prazer de receber a professora Sara Bals, da Universidade de Antwerp. Então, eu espero que todos aproveitem essa grande oportunidade. Vou passar agora a palavra para o Andrei, que vai fazer uma breve introdução e vai ser o chair dessa sessão. Então, obrigado a todos pela presença e espero que tenham uma boa experiência, uma boa aprendizado hoje com nosso seminário. Pode falar aí, Andrei.
Bom, então, bom dia a todos. A gente vai dar início agora à aula magna da pós-graduação, como o professor Eduardo BD falou. Então, eu devo introduzir a professora em inglês ou em português, Eduardo?
Inglês. Pode falar em inglês agora.
Inglês, né? Okay, so I'll switch to English now. So it's my pleasure today to introduce to you Professor Sara Bals. She is currently professor at the EMAT group of University of Antwerp. This EMAT group is the Electron Microscopy Laboratory. It's one of the leading centers for this kind of technique in the world. And she got the PhD at the University of Antwerp. So please correct me if I'm wrong. I got your information online, but so then she got a PhD from University of Antwerp. Then she did a postdoc at the Lawrence Berkeley National Lab in the States at the University of California. And then she got back to University of Antwerp. And she became research topic is electron tomography for nanostructured materials, which is the topic more or less that she's going to talk about today. And for which she received a ERC grant, starting grant, and more recently a consolidator grant. It's one of the most prestigious grants in Europe nowadays. She is also a member of the Royal Flemish Academy of Sciences, and she got the Microscopy Society of University and the ACS Nano Lectureship Award in 2021. She is part of the editorial advisory board of Journal of Applied Physics, and her H index is 65, so she's definitely one of the leading experimental researchers in this topic in the world now. So please, Professor Sara, you can start your presentation now. Thanks for accepting the invitation.
Well, I would like to start the presentation by thanking you for the kind invitation. It's a pleasure to be with you, even though it's virtual, and even though we started a little bit late. I hope you can hear me okay, and that you can see the slides and everything.
Yes, it's all fine now. Yeah.
Okay, good. Okay, good. So, well, as you can see, I will be talking about the three-dimensional characterization of the structure of nanomaterials under realistic conditions. And in fact, the motivation behind this project is the following. Nanomaterials consist of individual atoms. And so if we are able to determine the positions of the atoms, the chemical nature and the bonding between them, then we can provide the necessary input to predict their properties. And in this manner, we may even trigger the synthesis of novel nanomaterials. So we will tackle this challenge by first expanding electron microscopy from 2 to 3 dimensions. This is what we call electron tomography. Then I will show you how we can push the resolution of this technique towards the atomic level. And then I will discuss how we can not only investigate structure in 3 dimensions, but how to also extract information about composition and valence in 3D. And then in the second part of the presentation, I would like to discuss an ongoing project where we are combining the principles behind in-situ transmission electron microscopy and electron tomography. But let's start with the beginning. And here you can see a rather recent picture of our group in the pre-COVID times. Since then, the group has only grown even more. So you can see that this is quite a large group, all electron microscopists. So currently we have about 25 PhD students and 25 postdocs, and we also have a rather large technical staff, people that are helping us taking care of our instruments. At the moment, there are 6 transmission electron microscopes, 3 scanning electron microscopes, and 1 dual beam system. And this dual beam system is a combination of an ion beam and an electron beam. And we use this instrument to prepare lamellas such that they are thin enough to be transparent in an electron microscope. This picture here shows you a modern microscope, but still what I would call a conventional microscope. And in order to illustrate that, I would like you to compare this picture here to one of the newest members of the family. This is an aberration corrected microscope, and later on in the presentation, you will see why this microscope is so important if we want to investigate nanomaterials with atomic resolution. So this is how such a microscope looks like. It looks a little bit like a very large fridge or so. But what is inside? Well, let's have a look. You can see that in a transmission electron microscope at the top, we have a beam of electrons, and these electrons are guided through the stage by a series of electromagnetic lenses. At the bottom, we have a screen or a CCD camera capturing information in real space or reciprocal space. And here is where the interaction between the electrons and the sample takes place. Now, there are many types of interactions that can occur in a transmission electron microscope. And depending on the settings, the alignment, and the detector that we are using, we can get different types of information. Nevertheless, when I mention to people that I'm working in the field of transmission electron microscopy, people will think about images such as this one here. And obviously, this is a very nice image. It shows very high resolution. Every dot here corresponds to the position of an atomic column, and we can see a precipitate into a larger matrix. However, images such as this one here seem to suggest that a transmission electron microscope is simply a very good magnifying glass. And what I want to present today, or the point that I want to make, is that there is much more than the magnifying glass. And we cannot only obtain structural information, we can also obtain information about composition and valence by using analytical techniques. A first technique is illustrated here. This is energy dispersive X-ray spectroscopy. So the idea is that the electrons interact with the material, and because of that interaction, X-rays are generated. Now, if we investigate the energies of the generated X-rays, we can determine which elements are present in our sample. And we can also map that. For example, here you can see that we have investigated an iron cobalt nanoparticle, and we can spatially distinguish between the different elements. And if we look a little bit closer, we can also see that some oxidation of the system took place. An alternative is the use of EELS, which is the acronym for electron energy loss spectroscopy. The idea is that, again, the electrons interact with the sample. There are elastic interactions, but also inelastic interactions. And for the inelastic interactions, the amount of energy that has been lost is typical for the elements that the electrons have interacted with. So here at the bottom, we will have a magnetic prism that will spread the electrons depending on their energies. So we can again look at composition, but if we investigate the fine structure of these EELS spectra, we can also extract information about valence. And this is what my colleagues now did more than 10 years ago. So for example, here for this cerium oxide nanoparticle, they investigated the transition between cerium 4 plus and cerium 3 plus when moving from the bulk towards the surface of this catalytic nanoparticle. And so that is really of interest to understand the physical properties of this material. So a first evolution in the field of transmission electron microscopy is an evolution from structural information to more complete information about structural composition and valence. A second evolution is illustrated here. And the idea is that we are no longer interested in just looking at nice images. What we want to do is we want to translate our images into numbers. And in Antwerp, quantification is a field of expertise of my colleague Sandra van Aert. And using what is called statistical parameter estimation theory, Sandra and her team are able to determine the positions of the atomic columns with picometer precision, or as illustrated here for this gold nanorod, they can count how many atoms we have in a given atomic column. So this is all very nice and impressive, and you may start to wonder what my role in the group is. Well, the answer to that question is presented here. You see here a two-dimensional projection image of an unknown three-dimensional object. I do not think that many of you could have guessed that three-dimensional object in this case is a pile of trash. And so the take-home message of this presentation is that a two-dimensional projection of a three-dimensional object can be very misleading. This, of course, is a very extreme example, but it is a consideration that we need to bear in mind when analyzing any electron microscopy data. For example, here you see an old image of a gold nanoparticle. It's sitting on a magnesium oxide support. And even though this is a very nice image and again acquired at very high resolution, it is nothing else than a two-dimensional projection of an unknown three-dimensional object. Now, if we want to determine the three-dimensional object, we need to apply electron tomography. And the concepts behind this technique are illustrated here. So as I said, we are interested in the three-dimensional structure of a nanomaterial, in this case, a nanostar. And we will start the experiment by collecting two-dimensional projection images of this object using the transmission electron microscope and using a dedicated electron microscopy holder, which we're going to tilt in the microscope over a tilt range as broad as possible. Images are acquired every other few degrees. This will result in what we call the tilt series of images. We will be aligning the images with respect to each other, and they will serve as an input for a mathematical algorithm that enables us to obtain a three-dimensional reconstruction of our object. Now, we cannot only reconstruct the morphology of the object, we can also investigate the inner structure, which is illustrated here by what we call orthoslices. Now, over the years, we have applied electron tomography to a very broad range of materials, and I'm showing you two examples, an old one and a new one. On the left, you can see what is called an assembly of nanoparticles. But it is clear that from such a two-dimensional projection image only, it is impossible to count the number of particles or to determine interparticle distances. And it is only after applying electron tomography that we can see how nicely these so-called gold nanodumbbells are stacked together as a three-dimensional puzzle. On the right is a more recent example. This is a three-dimensional reconstruction of a gold nanoparticle. And here we were particularly interested in the surface structure because you can see these grooves here. And we could determine that this particle yields some chirality. And indeed, aspects such as chirality or handedness are very difficult or even impossible to determine based on single two-dimensional projection images only. Now, these examples already indicate the potential of electron tomography, but these results have been obtained with a resolution at the nanometer level. And for many years, it was the ultimate dream to also visualize individual atoms in 3 dimensions. And so here is my personal journey in the field of high resolution electron tomography. And we started with very simple structures, which are illustrated on the left. These are gold nanorods. And we wanted to determine the type of surface facets. Now here you can see slices through that three-dimensional reconstruction. So everywhere where you see a dot, this is where an atom is located. And we were very excited that we were able to reproduce the lattice of the gold and that we could indeed measure surface facets. Now, of course, it's not from scientific point of view very exciting to reconstruct a perfect nanosystem. So this is why we went a little bit further and we investigated these gold decahedra, which are illustrated in the middle. Now, such gold decahedra are very interesting because they have this five-fold symmetry. So you have a five-fold twin here in the middle, and you have sort of a forbidden symmetry, which is causing a lot of surface strains because these segments need to close. So these systems have been investigated quite a lot. And the investigation of strain has been a very important topic. Now, when people are trying to extract information about strain from transmission electron microscopy images, they typically start from images such as this one here, and then they apply some sort of quantification procedure. So again, in collaboration with the group of Sandra van Aert, we have measured the positions of the atoms from this image, and then we have looked at, for example, possible changes in interatomic distances. However, if you look at these results, you cannot see anything in particular. And that's not surprising, because this image is again a average image. It's a two-dimensional projection of a three-dimensional object. So a lot of information is averaged over that third direction. So what we really need to do is, if we want to measure strain at the nanometer level, is we first need to perform a three-dimensional reconstruction. And then we need to look at virtual slices through that 3D reconstruction and use that as an input for strain measurements. So that is exactly what we did. Now, here is a reconstruction of this gold nanodecahedron, and there are more than 90,000 atoms in this nanoparticle. So you can imagine that doing such a reconstruction, in fact, is far from straightforward. And you can understand this because, mathematically speaking, this is simply an ill-posed problem. You have way more unknowns that you have equations in this case than you have experimental data. So in order to obtain a reconstruction such as this one here, we very often are going to use constraints or prior information that we have available on the system. So in this case here, we assume that every atom can be modeled as a three-dimensional Gaussian distribution. And because we can make that assumption, which is a fair assumption, a problem or inverse problem becomes sparse. So that means that it's easier to solve. And in addition, we are no longer reconstructing a data set of gray levels. We are reconstructing the positions of all of the atoms because we are simply need to determine the position of all of those Gaussian distributions. So in this manner, we could take virtual slices through the reconstruction. So we looked at one of these segments here, and then a slice through it, which is illustrated here. And now you can see that if we only look at one slice through the reconstruction, that there is a very clear trend in terms of lattice parameters. And we can see that there is an elongation of the lattice parameter when moving from the middle of the particle towards the surface. And we can also see that if we look along the direction of the original electron beam. And so that is clearly a sign of surface relaxation. Okay, so an even more recent example of high resolution electron tomography is illustrated here on the right. And this is in fact work done by my previous PhD student, Thais Milagres de Oliveira, who obtained her bachelor and master degree at the University of Minas Gerais, if I pronounce that correctly, where she has worked under the supervision of Carla Bazuwait, who has been the president of the Brazilian Microscopy Society. So what Thais and colleagues have investigated is the welding of gold nanorods upon femtosecond laser irradiation. So you see that because of the irradiation that nanorods will start to couple in different configurations, and we decided to investigate the configuration at the top in a little bit more detail. So we applied electron tomography to such a configuration, and here you can see the neck between the two gold nanorods. This is again a slice through the reconstruction. So again, every dot now corresponds to the position of an atom. And what was very interesting is that from this reconstruction, we could visualize individual defects. In yellow, you can see the presence of two dislocations. Now, we know that deviations from a perfect structure will influence the physical properties. So we thought, can we also investigate this in a little bit more detail? Now, remember that I told you about EELS, the electron energy loss spectroscopy technique? Well, if we go to the regime of the spectra, where we look at low energy losses, we can map the plasmon resonances of this system. And so you see here different peaks, and they each correspond to a different plasmon mode. And now we're going to focus on this one here, which is a CTP mode, which stands for charge transfer plasmon mode. That basically tells us how well the electrons can move from one rod to the other. Now, it is interesting that if we map this charge plasmon, a charge transfer plasmon, for a welded system, here illustrated on the right, and now a single crystalline gold nanorod with the same overall aspect ratio, that we see a broadening in the plasmon peak for this welded nanosystem. And that we could, with the help of simulations, relate to the presence of this dislocation. So I really like this example because it is showing that this high resolution electron tomography is a very precise technique. We can pick up individual defects, but by using other electron microscopy modes, we can also directly couple that to the physical properties of this system. Now, these systems that we have been investigating are gold nanorods, and gold behaves rather well in the microscope. It's relatively stable, but that is not always the case. For example, here you are looking at a lead selenide superlattice. So we see these quantum dots. And we see that there's an amazing long range order for this assembly. Now, the quantum dots are connected to each other using oriented attachment, and we wanted to investigate that interface between those particles in a bit more detail. Now, the problem is that these materials are extremely sensitive to the electron beam. So basically, you acquire one image, and that's all. You completely damage the structure. So there's no way that we can perform our conventional tomography approach where we acquire hundreds of images of the same area of interest. Now, in order to still obtain a three-dimensional model for these systems, what we do is we acquire one high-resolution image. Again, using quantification, we count the number of atoms in every atomic column. And from this, we build a starting configuration. And this starting configuration, in fact, we assume that there is symmetry along the z direction. Then we allow our system to relax, in this case here using a simple Lennard-Jones potential. And this is then what we assume to be our final configuration, from which we can here see that the interface between the nanoparticles is formed through a necking process. So this is an approach that we use in situations where we cannot acquire conventional tilt series for tomography, either because the samples are too sensitive or because of other reasons that I will discuss later in the presentation. Okay, so I think I've shown a couple of examples where we can indeed see that using electron tomography, we are able to determine the positions of the atoms. But as I said before, it is also important to characterize chemical nature and bonding. And this is especially the case because nanomaterials become increasingly more complex, and very often they consist of more than one type of element. An example is presented here. These are gold, silver, coarse nanodots. So these images, they have been acquired using a technique that is called high-angle annular dark field scanning transmission electron microscopy. So let me explain this quickly. We have a focused beam, and we use this focused beam to scan across an area of interest. And then we use a ring-like detector, an annular detector, to collect the electron scatter to high angles. Now, this type of scattering resembles Rutherford scattering, and the intensity in the images will scale with the atomic number z squared. And that is the reason why the gold appears with higher intensity in comparison to the shell of these core shell structures. So we have been able to investigate these systems at high resolution. And again, we were able to perform high resolution electron tomography. We can reproduce the lattice of the silver and the gold, and we devoted special attention to the interface between the core and the shell. Now, because of the Z dependence, you can see that we have roughly two classes of gray levels, which we could quantify. And in this manner, we can color code our image, and we could determine which type of crystallographic facets we have at the interface between the core and the shell. Now, these systems are, I would say, relatively easy in a sense that gold and silver are far away from each other in the periodic table. So you have a lot of contrast, and also the interface between both materials is very sharp. However, if you want to look at systems with elements closer to each other, such as, for example, iron cobalt, we need to look for alternatives. And so one of these alternatives is the use of EDX, which I already explained before. So what I showed you before was just one EDX map, which is shown here again at the bottom. And what is shown at the top in the yellow color is a three-dimensional reconstruction obtained using electron tomography if we would use this HADF stem reconstruction. You can see that we do not see contrast, and the reason is that cobalt and iron are next to each other in the periodic table. However, if we acquire EDX maps, and if we acquire a tilt series of EDX map, we can use that as an input for 3D reconstruction, and then we can obtain a three-dimensional reconstruction of also the distribution of the different elements. And then what you will see in that reconstruction is in fact that the iron cubes have overgrown the cobalt rod, and that is information that is difficult to obtain using other electron tomography techniques. Now, if you want to really quantify this approach, it becomes a little bit more complicated, and I do not have time to go into that, but here are two references where this is explained in more detail. Okay, now you may wonder if we can also use eels as an input for electron tomography, and the answer is yes, we can. For example, here what you see is in fact a four-dimensional data set, because every voxel, a voxel is a three-dimensional pixel, in this reconstruction contains now one of these eels spectra. And we can map the spectra, fit the spectra to reference spectra, and in this manner we could, for example, see that if we look at a purely octahedral nanoparticle, that this layer of cerium 3+ that we detected has equal thickness for the entire nanoparticle. However, if we look at a truncated octahedral particle, then we see that exactly here at this 100 facet, we have a much thicker cerium 3+ layer. That is very important because it contributes to the understanding of the preferential catalytic behavior of specific reactions according to the type of surface facets that are present. And here is another more recent example where we investigated an iron oxide nanostar. These are used for hyperthermal cancer treatment. And we wanted to distinguish between the core and the shell. These are two different iron oxide phases. And very often, this is very difficult to do because you can see here that specific iron oxide nanophases have very resembling lattice parameters. So here we made a difference by looking at the difference in the valence. All right. So you will think, okay, everything is solved. We have the positions, we have the chemical nature, we have the bonding. However, it's very important to point out that all of these investigations have been done under the conventional conditions of a transmission electron microscope, which means ultra high vacuum and room temperature. And those conditions are no longer sufficient if we think about the applications of these nanomaterials. And so therefore, a next challenge in the field of three-dimensional characterization is to again extract these parameters, but now under more relevant conditions such as high temperature, or for example, in a gaseous environment. And so in this manner, we want to mimic the conditions, for example, during catalysis or during photocatalysis, and understand the behavior of these nanomaterials. Now, performing in-situ transmission electron microscopy can be done using dedicated environmental microscopes. But in Antwerp, we do not have such a microscope. What we do have is a very broad range of dedicated holders. These holders are based on MEMS devices on chips, and they transform the microscope into a true nanolab, because by using such chips, you can heat or cool your sample, you can apply a strain, you can apply bias, and you can create liquid and gaseous environments. Now, unfortunately, performing a three-dimensional characterization using such holders is not a simple matter of plug and play, and there are several fundamental aspects that we need to overcome. And one of the most important aspects is related to the acquisition of a tomography tilt series. So I showed you this movie before, and you can see that in between every acquisition, the holder stops for a while. And while the holder pauses, we adjust the focus, we adjust the field of view. And in this manner, it takes about 1 hour to acquire a full tilt series of images, even for a trained user. Now, 1 hour is, of course, way too long to capture the fast changes that these nanomaterials will undergo when they're exposed to realistic environmental conditions. So what we are doing currently is, rather than capturing individual images, is we simply leave our holder tilt continuously and we acquire a movie. And in this manner, we can drastically accelerate the acquisition of a tilt series, and we can acquire such a tilt series in a few minutes only. To illustrate this, here on the left, you can see a gold nano dumbbell, which was reconstructed using a tilt series that was acquired conventionally in 1 hour. And then in B, you can see the same gold nano dumbbell, but now a reconstruction based on 6 minutes. So this is how such a tilt series looks like. In reality, we adjust everything on the fly. You see there are some distortions, but we have so many images that we can simply leave out distorted images and without compromising the resolution. Because you see, if I compare both reconstructions, I have very good agreement. So that means that this fast tomography is of great interest if we want to improve the throughput of electron tomography, if we want to investigate, let's say, 100 nanoparticles, if we have samples that are very sensitive to the electron beam, but also if we want to combine 3D characterization with environmental triggers. So for example, here we have a gold nanostar, and this nanostar has sharp tips, and these sharp tips are of importance during catalysis and sensing. But we now want to understand what happens to those tips at a high reaction temperature, or when this nanoparticle would absorb heat, for example, because of laser illumination. So the experiment we performed is the following. We start at room temperature. We acquire tomography tilt series. We perform a reconstruction. Then we have a dedicated heating holder that can tilt in the microscope. So a heating tomography holder. We're going to heat it to 200 degrees Celsius. We keep it there for 30 seconds. We quench the system in the microscope and we acquire another fast tomogram. And because these tilt series for tomography can now be acquired in a few minutes, we can continuously repeat this process and we can very accurately see what is happening as a function of heating time. We can also perform these experiments at different temperatures. And every time what we see is that the sharp tips disappear very quickly. And that will certainly influence the physical properties of these materials. We can also go ahead and we can quantify this. Here you see in red where volume is disappearing. We can see in green where the volume is growing. And we can also look at the redistributed volume as a function of heating time. And now we see that most of the changes happen in the first few minutes. So keeping this in mind, we performed another experiment where we're now going to look at gold palladium octapods, and we're going to be investigating one and the same particle, but each time we're going to increase the temperature. So we start at room temperature, then we go to 200 degrees Celsius, acquire a tomogram, a quench, we go to 250, and again at every temperature, we keep it there for a minute and a half or so, just to make sure that all of the changes have appeared. And because we can acquire the tomograms in a few minutes only, we can continuously repeat this process. And again, you can see that the sharp tips are becoming blunt. This starts to happen around 400 degrees Celsius. And again, we can connect that to the optical properties because again, we can perform plasmon mapping. And then you can see that the intensities in these plasmon maps is dropping as sharp tips become more blunt. And this is quite expected. We also compared with pure gold octapods, which are shown here in red and in blue. You can see that they are much less stable. And so that means that the palladium is really contributing to the thermal stability of these octapods. Now, these are bimetallic systems. And so we thought maybe we can also investigate composition at high temperature. And so again, we selected a sample such as this one here, which I already discussed before. And the interest for this sample is that the tunability of the optical properties depends on the shape of these nanorods, on their aspect ratio, but also on the shell thickness. So we wanted to understand if the shell remains at higher temperature. Now, the answer is very clear, no. Very quickly, an alloyed system is formed. and we wanted to investigate alloying in a little bit more detail. So what we're going to do here is in A, you see a virtual slice through a three-dimensional reconstruction at room temperature. And if we plot the voxel intensities, we see two peaks, again, because this tilt series was acquired using high angular dark field STEM. So we see a peak corresponding to pure gold, and we see a peak corresponding to silver. Now, if we keep on tracking the same nanoparticle, and every time we heat, then it's a fair assumption to say that the gray levels will always be a linear combination of these two original intensities. And so in this manner, we can quantify our three-dimensional reconstructions, and we can follow the alloying process. So we did this for 3 different systems. We have a core shell nanorod, and we have 2 core shell nanotriangles. And you will see that the nanotriangle on the right is slightly more asymmetric. And also the composition is a little bit different in contrast to the 2 particles, the one on the left and in the middle. The composition of this asymmetric nanotriangle has 70% gold, whereas the other ones have 60% gold. Now, our experiment is again the same. We're gonna perform electron tomography at room temperature. We're gonna go to 450 degrees Celsius. We keep it there for 30 seconds. We quench, we perform tomography, we heat, we quench, we perform tomography. And every time we also perform this quantification that I explained. And so here you can see the alloying taking place in these nanoparticles. And then if we compare the different systems, you see that alloying for the core shell nanorod and the symmetric core shell nanotriangle is more or less the same. However, the asymmetric nanotriangle starts to alloy much faster, and that can be due to the slight asymmetry or to the slight change in composition. But it is a motivation to perform these investigations really at a single particle level rather than using ensemble techniques. Now here we performed an additional investigation where we compared 6 different systems. We have here 2 core shell nanocubes with a different morphology for the core, and we have 4 nanorods. Nanorod 1 and 2 are single crystalline. They have a different aspect ratio. Nanorod 3 and 4, they are pentatwins. So they have a 5-fold twin in the core, which is for nanorod 3 a rod, and which for nanorod 4 is a bipyramid. And again, we compared the alloying, which is sort of the same for the nanocubes, independent on the type of crystallographic facets at the interface between the core and the shell. Also for the single crystalline nanorods, we could not see too much of a difference. But in nanorod 3 and 4, where we have this pentatwin structure, so where we have a lot of grain boundaries, we could see a much faster alloying. And that is also reflected here in the diffusion constants, which we extracted from our experiments. So apparently the presence of these defects is contributing to faster alloying, and that is something that we are currently investigating. Now, these results have been obtained using these holders, as I explained before, but using a holder that can really tilt sufficiently to acquire a tilt series of images. Now, as I said, this is not always the case. And for example, there are situations where a holder cannot tilt enough or where changes happen really fast. And so in order to investigate such situations, we return to this 3-dimensional modeling from 2-dimensional images, which I have explained before for the lead selenide lattice. So this is now a gold nanoparticle sitting on a cerium oxide support. Again, we counted the number of atoms and we used this as an input for molecular dynamics simulations to obtain a 3-dimensional model for our system. And using this approach, we made a comparison between these gold nanoparticles at room temperature and high temperature. On the left and in the middle, you can see 2 nanoparticles with more or less the same size. And we see that if we compare the 3-dimensional models at room temperature and high temperature, that the facets do look a little bit different. However, if we look at the coordination number of the individual atoms, we see that these graphs look very much alike. On the other hand, for these smaller nanoparticles, we see that at high temperature, a more rounded structure is formed. And this is also reflected here by coordination number 12, which is increasing, and coordination number 12 corresponds to bulk atoms. So we have a rounder structure and therefore more bulk atoms. And so the reason for this change is that there was a lot of strain present here for this flat nanoparticle. And so this strain is released once the particle has sufficient energy, for example, by heating. And then a final, I'm going to skip this slide. A final example is presented here where we are investigating platinum nanoparticles. Now, these particles are being imaged in a gas. And as a result, the image has worse contrast than the other images that I've shown so far. This is not surprising. Think about driving in the fog. So we acquired a series of images and we averaged them into an image from which we can again now count the atoms and use that as an input for molecular dynamic simulations. And now we have compared the structure for one and the same particle in vacuum and in different gaseous environment. And you can see that indeed the surrounding has a large effect on the surface structure. For example, in hydrogen, we see a nicely faceted surface structure, whereas in oxygen, we see a more rounded surface structure. And we could go back and forth between hydrogen and oxygen. We could see every time the facets, the more rounded structure, but we also notice here that the percentage of higher order index facets is dropping after a few cycles. And so that is important to take into account if one is going to be using these particles eventually during real catalytic processes. So that brings me to the conclusions. I've shown you that electron tomography can be used to determine the positions of the atoms in a nanoparticle, but also to investigate chemical nature and bonding in 3 dimensions. And nowadays, we are even able to perform 3-dimensional tracking of heat-induced changes in morphology, as well as composition. And we are able to investigate 3-dimensional nanoparticle dynamics in a gaseous environment. With that, I really would want to thank the entire team in Antwerp. I always say EMAT has the same letters as team, and all of this work is really the result of a great team effort, and I'm very grateful for that. I'm also very grateful to all of the collaborators, and especially those providing us with such nice samples. I am thankful for the financial institutions and you for your attention.
Okay, so thank you very much, Professor Sara Bals. It was a very nice presentation, very interesting results. So the session now I'm going to switch to Portuguese because maybe some of the students could be wanting to ask questions also in Portuguese, okay? So, então, pessoal, tá na audiência aí, se alguém quiser fazer alguma pergunta, pode fazer aí que a gente coloca na tela e aí eu posso traduzir para a professora, ou se vocês quiserem já escrever a pergunta em inglês, também pode ficar mais fácil, né? Bom, no chat, mas já tem a Isis está agradecendo antes, o professor... okay, now it's here in the screen. So, some thanks from the students to you. Maybe I should start already, maybe some questions. I have some. So, do you hear me? I think I lost
yes, sometimes I lose you a little bit. So if you ask a question, I didn't understand.
Oh, no, I didn't. Are crystals, right? So crystals that have different crystal structures in like domains or something, right? But I know that one of the things that people are very interested in different groups, especially in theoretical chemistry, is this formation of glass solids also with your take?
Right, that's a very good question. So the way to understand this, the more simple a crystal structure, the less projections one would need, right? So in principle, for example, the very first atomic resolution reconstructions that we did of these gold nanorods, there we only used 3 projection images because your structure is so well defined. So the less defined, the more images that one would need. And in principle, to investigate an amorphous structure, you would need an endless number of projection images. Now, the problem with these amorphous structures is that, well, first of all, they will be rather beam sensitive. And there is no way to check if atoms have moved while acquiring the tilt series of images. So looking at amorphous structures is extremely difficult, I would say, and currently it is not yet possible. However, we are developing a lot of novel techniques at low electron doses. And so maybe if we use those techniques in combination with electron tomography, that something like that will become possible in the future. But so at the moment, I would say it is very challenging. Something will come out of your experiment, but it will be very difficult to prove that it's really reliable.
Okay. And also, structures that change the composition or time, for example. And I know that there is some interest in the literature too about this 2D material called black phosphorus, because it's also elemental materials such as graphene or something, but it's made of phosphorus. But when you go for monolayer of this material, then it gets very unstable. So, for example, you make a measurement today, then if you do like a few hours later or maybe tomorrow or something, the results are different. So this is something that had people were a little bit less excited about this material because of that. But have you ever tried to check that, like maybe the changing composition of monolayer black phosphorus as a function of time, or is this too much a silly question? Or
no, I think in principle it's perfectly possible. For a monolayer of material, of course, there is not necessarily a need to do it in 3D. I think there you can use a simple two-dimensional projection image, so it would be much easier. We can put a sample in a holder, we can store the holder in vacuum, and we can look at it today and tomorrow and next week. So in principle, that is possible. I don't know if it has been done, but I do not see any fundamental reason why one could not do it. And then, of course, what would be nice is to do that under the relevant conditions again, because if we're going to do it in vacuum and at room temperature, it might not be very relevant for the storage conditions where people have seen this effect. So that is where a combination with in situ holders would probably be of interest.
Yes. Not exactly in the 3D reconstruction, but more like in the fact that you can control the environment and make videos of this thing. People could understand better what is happening, and then they could,
I think that should be totally possible. Yeah,
that would be very interesting to see. But it can be that it was already done. I'm not really sure.
Yeah, I'm not 100% sure either, but I do not see a reason why it could not be done. Yeah.
Yeah. Okay. Is also thanking you for your presentation. Say it's literally very beautiful work.
Thank you.
Yeah. Also, you showed in one of your results that you were comparing in a single sample. You have iron 3 and iron 4, I think. And you said that you compare these two by comparing the difference between the valence in these two. How did you get the valence? I think I missed this.
So we get the valence from so if you look at yield spectra, and if you look at the fine structure of the iron peak, it's a bit different depending on whether it's iron 2+ or 3+. So we have known samples where we know the valence for sure, and then we use some sort of fingerprinting to determine if in an unknown sample the valence corresponds to 2+ or to 3+. And so then we have a three-dimensional reconstruction. So every voxel contains an EEL spectrum, and we're going to fit that spectra to known spectra. And in this way, we are going to extract the valence. So it's based on the fine structure of EELs, which is called ELNIS, electron loss near, yeah, I forgot. But in fact, it's the fine structure of an EEL's spectrum. It resembles a bit like SANIS.
Okay, okay. And so one of our students has a question here. So how do you treat phase changes due to?
Yeah, so in none of the investigations that we have performed, there was an expected phase change, but it is something that can totally be done. And then the easiest thing is probably to look at the diffraction pattern, where you would see a change in symmetry or a change in lattice parameter. And sometimes people also use that technique in order to calibrate the temperature that they have in the microscope. If you have a system where you know that a specific phase transition will occur at a given temperature, then you know, okay, we are at, I don't know, 350 degrees Celsius, and you can see oversensitive material. None of the materials like gold stays, well, it starts to melt, which is what we have seen. But it starts to melt at temperatures much lower than the melting temperature of gold, by the way. But conventionally, all of the investigations at atomic resolution, they have been done at room temperature. So that is just room temperature, and the beam is going to heat the sample just a little bit, few degrees, but not too much.
Okay. Also brought me to the question of, you could maybe try to do that also at different, instead of different temperatures, trying different pressures too, right? I mean, if you
yes,
want
exactly,
to see
exactly,
different,
yeah, that's indeed.
Like for example, that we need to see in pressure.
Yeah, definitely. So that is also something that is totally possible. Yeah, there are so many possibilities available indeed.
Yeah, I just guess that it can be a bit problematic more in a practical too much pressure needed for the equipment that is maybe not easy to couple with what you already have there.
No,
right?
so these gas cell holders, they are in between two silicon nitride windows, and so we can apply a pressure up to 1 bar, which is quite good, indeed. But yeah, those are not the very complex, very easy experiments that you're going to do one afternoon. Then we really booked the microscope for an entire week to very carefully perform experiments, also taking safety considerations into account, of course.
Okay. So, are there more questions from the audience? Tem alguma pergunta mais da audiência? Just waiting for one minute here. Maybe somebody's writing something. Okay, then. So again, thank you very much. Bedankt.
Dank u wel.
So we're welcome if you want also to visit our university at some point. It would be very good also. So
I would love to. I've heard good things from the colleagues here at the physics department. So
yes, yes, I was there. Actually, we met once or twice in some defenses, but
could be. Yes,
I never. Yeah. I never went to the EMAT lab, and also because of the pandemic and so on.
Yeah, that's true. That's true. Always welcome.
Yeah. Okay, so thank you very much again. So I'm going to finish the broadcast now. Thanks for all the students and professors who are in the audience now. So we see you again in 2 weeks because next week is a holiday here. Okay, so
thank you.
Okay, thank you, Professor Sara.